Optimization often comes down to making the most profitable local choice without worrying about the steps ahead. We call this the greedy approach, and the classic way to understand it is the knapsack problem, maximizing the value of a bag that has a strict weight limit. This handwritten table sets up our specific scenario. We have a total knapsack capacity of 60 and 5 available items. The first step is to calculate the value-to-weight ratio for each item by dividing profit by weight. Once we have those ratios, we rank the items in descending order. Item 1 has the highest ratio, so it goes in first. Item 3 is next. We add these whole items, draining the capacity from 60 down to 35. We hit a constraint. Item 5 weighs 40, but only 35 space remains. We take the exact fraction that fits, 35 over 40 times 160. That yields 140, bringing the final profit to 270. By strictly prioritizing the highest ratio item at every single step, the algorithm mathematically guarantees the maximum possible yield for the available capacity. We apply that exact same logic to data compression using Huffman Coding. Here, the greedy strategy is to continually merge the lowest frequency data points together to create an optimal compressed structure. Look at this table showing character frequencies, arranged lowest to highest. Following the greedy method, we take the two lowest values, E at 4 and A at 5, and combine them into a parent node with a frequency of 9. This is where calculations derail. The combined node of 9 must be added back to the active pool as a single unit. Re-evaluating the pool, the two lowest values are now C at 7 and the new node EA at 9. Repeating that process until one final tree remains yields this completed structure. To generate compression codes, trace branches top to bottom, assigning 0 to left paths and 1 to right paths. Character F becomes 0, 0. Character E becomes 1, 0, 1, 0. Because we greedily merged the smallest components first, the most frequent characters naturally land closer to the top, securing the shortest possible binary codes and ensuring no code is a prefix of another. When we need to find an optimal path but can't use fractional solutions, computing every single outcome is a massive waste of processing power. Instead, we use branch and bound to calculate cost limits and safely ignore bad paths. This matrix assigns 4 workers to 4 jobs, aiming for the lowest total cost. To establish a baseline, we calculate the cost bound if worker A takes job 1. That costs 9. We then add the absolute minimum possible costs from the remaining rows, 3, 8, and 4. That gives us a starting bound of 24. But watch what happens if worker A takes job 2 instead. That costs 2, and it completely locks out column 2 for everyone else. Worker B's minimum available job is now job 3, costing 3. Worker C's minimum is job 1, costing 5. Worker D takes job 4, costing 4. That gives us a much lower bound of 14. We map these bounds on a branching tree. Now test yourself. Pause the video. If worker A is locked into job 2, calculate the new bound if worker B takes job 1. Remember to lock out rows A and B and columns 1 and 2.
allowing us to drop them entirely without running the full computation. When an algorithm hits a dead end in a logic puzzle where pieces interact, we rely on backtracking, a cycle of trial, error, and precise state resets. The 4 queens problem maps this perfectly. We have to place 4 queens on a 4x4 board with no horizontal, vertical, or diagonal attacks. We place queen 1 at position 1-1. Queen 2 safely lands at 2-3. But immediately we hit a wall. Looking at row 3, the first 2 queens have projected attack lines covering every single square. There are no safe spots. This is the undo phase. The algorithm removes the stuck piece, steps backward to the previous piece, and shifts it laterally to the next available option. Queen 2 moves to position 2-4, shifting the attack lines and clearing space on the row below. With that state reset, Queen 3 cascades safely into position 3-2, and queen 4 slots into 4-3. Our final output array reads 2, 4, 1, 3, representing the safe column for each successive row. Backtracking systematically burns through massive search spaces by recognizing failure early, stepping back exactly one level, and trying the next viable path. Let's lock in the mechanics for all three paradigms. For the greedy approach, always calculate the immediate value ratios, sort them descending, and if allowed, slice the final item to perfectly fill the constraint. For branch and bound, sum the row minimums to establish an absolute baseline cost, lock out your chosen columns, and solely expand the lowest resulting number. And for backtracking, advance until you collide with a rule constraint, step backward exactly one sequence level, and shift to the next lateral option.
Understanding these three distinct mechanical processes allows you to approach complex algorithmic constraints not with guesswork, but with systematic, provable logic.